Let's talk about eigenvalues and eigenvectors. In some applications, we are interested in a vector x, such that ax equals lambda x for some scalar lambda. Lambda is a Greek letter, it's the equivalent of our L. An eigenvector of an n by n matrix A is a non-zero vector x, such that ax equals lambda x for some scalar lambda. The scalar lambda is an eigenvalue of A. We need to see an example. Let A equal 1, 6, 5, 2, x equals 6, negative 5. Is x an eigenvector of A? It's an eigenvector of A if ax equals lambda x for some scalar lambda. Let's calculate it. Here's ax. Multiply it out, you get negative 2420. Hey, notice, that is a multiple of x. It's negative 4 times our vector x. It's negative 4 times 6, negative 5. So x is an eigenvector of A, and lambda equals negative 4 is the corresponding eigenvalue. How about x equals 1, 2? Is x an eigenvector of A? Let's check it out. Ax, when you multiply it out, is 13, 9. Oh no, that doesn't work out at all. That is not a multiple of 1, 2 for any scalar. It does not equal kx for any scalar k. So x is not an eigenvector of A. Here's how to find eigenvalues and eigenvectors. We're looking for non-zero solutions x to ax equals lambda x. Let's get everything on one side. It is so tempting to factor out x and say, okay, so now we've got a minus lambda times x equals 0, but that's wrong. That makes no sense at all, because you can't have a minus lambda. A is a matrix, lambda is a scalar. It's a constant. You just can't do that. Here instead is what we can do. We're going to rewrite lambda x as lambda I times x. Here I is the identity matrix, because multiplying a vector x by a constant lambda is the same thing as multiplying the identity matrix by lambda and then taking that resulting matrix and multiplying it by the vector x. That'll give you the same result. And now we can factor out x, because both A and lambda I are n by n matrices. Okay, we know x equals 0 is the solution. There are non-zero solutions x if and only if the determinant of A minus lambda I equals 0. We've seen this before, that an equation like this has a non-trivial solution x if and only if the determinant of this thing is 0. So that's what we're going to try to do. We're going to try to solve determinant of A minus lambda I equals 0. The values of lambda for which determinant of A minus lambda I equals 0 are the eigenvalues of A. Once we know these, we can find the values of x for which A minus lambda I x is 0. Those will be the eigenvectors. So find the eigenvalues and the corresponding eigenvectors for A equals 7, 4, negative 3, negative 1. We find the eigenvalues by finding the determinant of A minus lambda I and setting it equal to 0. Okay, we know what I looks like. I is just going to be 1, 0, 0, 1. Okay, you multiply that by lambda, and then you're just going to get lambda 0, 0, lambda. So you subtract that from A, and you're basically subtracting lambdas from the diagonal. So the determinant of A minus lambda I is the determinant of 7 minus lambda, 4, negative 3, negative 1 minus lambda equals 0. We know how to calculate a determinant. Product of these minus the product of these. That's going to be negative 7 minus 6 lambda plus lambda squared plus 12 equals 0. When you multiply it out, simplify, and you get lambda squared minus 6 lambda plus 5 equals 0. So this is the determinant of A minus lambda I, which we call the characteristic polynomial for A. Eigen is German for characteristics. So we have eigenvectors, eigenvalues, but we have a characteristic polynomial. It is the polynomial determinant of A minus lambda I. So let's factor that. Set it equal to 0, we factor, we get this. So it looks like the solutions are going to be lambda equals 5 and lambda equals 1. Thus, the eigenvalues are lambda equals 5 and lambda equals 1. Now let's find the corresponding eigenvectors for each eigenvalue. These are the values of x for which A minus lambda I x equals 0. Let's go ahead and find those values of x. So A minus lambda I x equals 0. First, what happens when lambda equals 5? Plug in lambda equals 5 into here, and we get this 7 minus 5, 4, negative 3, negative 1 minus 5 times x equals 0. Simplifies to this. There's the augmented matrix. Get it in reduced echelon form. That's what we have. So this is x1 plus 2x2 equals 0. In other words, x1 equals negative 2x2. So x1 is negative 2x2. x2 is simply x2. Therefore, x1, x2 is x2 times negative 2, 1. any multiple of negative 2, 1 is a solution. So this is an eigenvector for the eigenvalue lambda equals 5. How about for the eigenvalue lambda equals 1? Again, let's solve this. Plug in lambda equals 1. This is what we'll end up with. 7 minus 1, 4, negative 3, negative 1 minus 1. That simplifies to 6, 4, negative 3, negative 2 times x times x1, x2 equals 0. Here's the augmented matrix. This is what the reduced to echelon form of that matrix looks like. So we have x1 plus 2/3 x2 equals 0. In other words, x1 equals negative 2/3 x2. So x1 is negative 2/3 x2. x2 is simply x2. Therefore, a solution is x1, x2 is x2 times negative 2/3 x1. So any multiple of negative 2/3, 1, is a solution. So this is an eigenvector for the eigenvalue lambda equals 1. Find the eigenvalues and corresponding eigenvectors for a equals 1, 2, 0, 8. Determinant of a minus lambda I, again, we just subtract lambdas from the diagonal, and we multiply it out. This is what we end up with when we calculate the determinant. Oh, we know how to solve that. The solution to this is just lambda equals 1, lambda equals 8. Those are the eigenvalues. See, this is something we could have seen much more easily. This is an upper triangular matrix. For a triangular matrix, whether it's upper triangular, lower triangular, or diagonal, the eigenvalues are the entries along the diagonal. So when we see a matrix like this, we immediately know that the eigenvalues are going to be 1 and 8. Find the eigenvalues and corresponding eigenvectors for a equals this monster 3 by 3 matrix. 4, negative 1, 6, 2, 1, 6, 2, negative 1, 8. Again, we want to solve determinant of a minus lambda I equals 0. Method 1, you can do this on the TI-83. So this is pretty cool. It's pretty crafty. What you would do is go to y equals and just graph the determinants. So basically, you would graph the determinant of a. Essentially, we're going to graph determinant of a minus lambda I equals 0. So here's the way we do that. Y equals determinant of a minus x times the identity of 3. This, again, is the matrix A. You'd have to enter that beforehand. X, you know where to find that on the TI. This is just under matrix. It's the 3 by 3 identity matrix. So basically, this can be entered like this on your TI-83. And you just graph it and see where it's 0. It turns out it's 0 at x equals 2, x equals 9. Now, to be honest, if you have a TI Inspire, it just has an eigenvalue and eigenvector command, so you can do it like that. It's much quicker. But you can do it using the old-fashioned TI-83, as you can see. Here's method 2. Okay, this is the long way to do it. Determinant of a minus lambda I, you subtract lambdas from the diagonal. This is what you end up with. And then you just evaluate this determinant. We're just going to expand along the first row. We know how to evaluate a 3 by 3 determinant. That's what we get. You spend the next 5 hours simplifying, and okay, this is what you're going to end up with. You get this, which simplify, and you just multiply it out. Just multiply everything out. You get this, simplifies to that. Okay, which simplifies to this. I don't know if it simplifies the right word for it. Okay, multiply it out, we get this. Okay, this turns out to be factored as negative lambda minus 2 squared times lambda minus 9 equals 0. Therefore, the characteristic polynomial is the opposite of lambda minus 2 squared times lambda minus 9. So lambda equals 2 is an eigenvalue with multiplicity 2 since it appears twice here, and lambda equals 9 is an eigenvalue with multiplicity 1. Let's find the eigenvectors for A. First, lambda equals 2. Plug in lambda equals 2 here. Plug in lambda equals 2. We end up with this. Get in reduced, we're going to get that in reduced row echelon form. There's the augmented matrix. Reduced row echelon form simplifies to this. So we have x1 minus half x2 plus x3 equals 0. Or in other words, x1 equals half x2 minus 3x3. Therefore, x1 is half x2 minus 3x3. x2 is x2. x3 is x3. We can separate this out. This is the x2 stuff. This is the x3 stuff. So it equals x2 times 1 half, 1, 0, and x3 times negative 3 is 0, 1. There are two eigenvectors, 1 half, 1, 0, and negative 3, 0, 1. The set of all solutions looks like this. Okay, so it's going to be x2 times this plus x3 times this. Or you could just say it's the span of those two vectors. So the set of all solutions to A minus lambda I x equals 0 is called the eigenspace of A, corresponding to lambda equals 2. It's a vector space because it's the span of a set of vectors. How about lambda equals 9? Plug in lambda equals 9, and we end up with this. Here's the augmented matrix. Get it in a reduced echelon form. That's what we end up with. So it looks like we have x1 minus x3 equals 0 and x2 minus x3 equals 0. In other words, x1 equals x3, x2 equals x3, x3 equals x3. That can be simplified to x1, x2, x3 equals x3 times 1, 1, 1. There's only one eigenvector, 1, 1, 1. Suppose that 0 is an eigenvalue of the matrix A. This means there is a non-zero solution to x to ax equals 0x. In other words, there is a non-trivial solution to ax equals 0x. What does this imply about A? By that monster theorem we saw, which is this long collection of things that are equivalent to the matrix A is invertible. By that monster theorem, A is not invertible. Add this to the monster theorem. A is invertible if and only if 0 is not an eigenvalue of the matrix A. The set of all eigenvectors for a matrix is linearly independent. Find the eigenvalues for this matrix A. -2, -1, 5, 2. Okay, let's do this one. So find the determinant, set it equal to 0. Oh, let's multiply it out, solve. Ooh, a lambda squared plus 1 equals 0. Lambda equals plus or minus I. Thus, we can have complex eigenvalues. We will see these in differential equations. It's just hard to believe that there would actually be an application for complex eigenvalues, or complex numbers for that matter, but there really are. There is another way to obtain the characteristic polynomial for a 2 by 2 matrix. The characteristic polynomial for a 2 by 2 matrix A is lambda squared minus the trace of A times lambda plus the determinant of A. Let's verify this for a matrix we saw earlier, 7, 4, -3, -1. The trace is 6. The determinant is 5. Again, 6. It's just the sum of these two. The determinant is 5. You can calculate that. And the characteristic polynomial is indeed lambda squared minus 6 lambda plus 5 equals 0, as we saw earlier. Let A be an m by n matrix, then the determinant of A is the product of the eigenvalues of A, and the trace of A is the sum of the eigenvalues of A, repeated according to multiplicity. Verify this for a matrix we saw earlier, that matrix A. Okay, the eigenvalues were lambda equals 2, 2, 9. Remember that lambda equals 2 is an eigenvalue with multiplicity 2. We saw that a moment ago. The determinant of A, yeah, you'd multiply that out, and you'd end up with 36. So this is indeed the product of the eigenvalues of A. So 2 times 9 is indeed 36. So it did work out that way. And the trace of A, 4 plus 1 plus 8, is 13. This is indeed the sum of the eigenvalues of A. 2 plus 2 plus 9 equals 13. If lambda is an eigenvalue of A with corresponding eigenvector x, then lambda to the k is an eigenvalue of A to the k with corresponding eigenvector x. Verify this for a matrix we saw earlier. A equals 7, 4, -3, -1, for k equals 3. Okay, so yeah, the eigenvalues, we know those. That's lambda equals 5, lambda equals 1 with those corresponding eigenvectors. Thus, the eigenvalues of A cubed, we just picked A cubed randomly, should be lambda equals 5 cubed, in other words 125, and lambda equals 1 cubed equals 1 with corresponding eigenvectors -2, 1 and -2/3, 1, as we saw earlier. Let's confirm this. Okay, A cubed, it looks like this. When you multiply it by -2, 1, notice what you end up with. Do all the math. You end up with -250, 125, which is 125 times -2, 1. Therefore, A cubed has an eigenvalue, lambda equals 125, with corresponding eigenvector -2, 1. Similarly, A cubed times this matrix, yeah, that just works out to be -2/3 times 1. Hey, that is, yep, works out nicely. Therefore, A cubed has an eigenvalue, lambda equals 1, with corresponding vector -2/3, 1.